Okay, so today we'll finish up our aromatic compounds. And so on Friday, at the end, we were looking at saying, okay, if we have a phenol, how do we convert the phenol to an ester? If we have an amide, if we have an amine, how do we convert the amine to the amide? And then I left you with the last one, which is how would we convert a phenol into a let's say something like that ether. Because once I put the OH or the NH2 on the ring, I may want to change it over to those. So we basically said that for making an ester, we could use either the carboxylic acid and acid, do Fischer esterification, or we could do an acid chloride. And either one of those would make the ester. We could use an acid chloride for the amide, so reacting an amine with an acid chloride is probably the easiest way to make an amide. And then I left it for you to ponder how we would make an ether. Did anybody ponder that question over the weekend? Did you ponder it over the weekend, David?
When I was doing that quiz.
When you were doing the quiz. Oh, okay. So what do you suggest? So we could do a Williamson ether synthesis. What's that? I forget. What do I want to do first for the phenol? Deprotonate it. So we'll deprotonate the phenol. And then react it with primary or secondary alkyl halide. And that would give us our ether. What can I use to deprotonate the phenol? Somebody give me a reagent. You've answered enough for the time being. Let's see, what do I have to do? Anybody got an answer? Jacob?
Did you do the liquid ammonia?
How about just an NH2 minus? Or a... No. It's got to deprotonate. I've gotten deprotonating VOH, so I don't need an acid reagent, I need a base. What other base will deprotonate an OH? I got an N minus. Yes. In this case, a terse butoxide would work, but normally that would not deprotonate a regular alcohol. So it only works in this case. So an alkoxide, I've got an NH2 minus. What else? N minus. C minus. H minus. Sodium hydroxide would work. This is a phenol. So phenol is more acidic because of the resonance structures that you get. The O minus, there is now 3 more resonance structures you can draw for that deprotonated phenol. So phenol is more acidic, which means it will be deprotonated by an alkoxide. It also would be deprotonated by a simple sodium hydroxide. Okay. And the restriction here is primary or secondary because Williamson, this is the Williamson ether synthesis. Because the Williamson ether synthesis is what kind of reaction. If this is a primary or secondary halide, this mechanism is SN it's either SN1 or SN2. 2, we agreed it's 2. What happens if I try and do this with the tertiary halide? What mechanism am I going to get? I'm going to get a mechanism. David, is that what you were going to say, Aisha? E2, do we agree with that? We would get an E2 reaction. All right, we have to remember all of this. If it wasn't going to be on Friday's test, it's now relevant, so it could be. So let's see how much more stuff I can jam in for Friday's test. I'm sort of kidding. Sort of kidding there. Okay. All right, so that's, we need to be able to do these 3 reactions in order. Once I get an OH, once I get an NH on the ring, I have to be able to convert it over to an amide ester or potentially make an ether. So this is how I would do that. All right, so, oh wait. There's a couple more things here that I can do. They're metals. Or sodium or potassium. Metal. That would also work. Yes, it would. Okay, other reactions of phenols. There's a very nice reaction that if you have a phenol, you can react it with carbon dioxide and sodium hydroxide. And you can end up adding the CO2 onto the ring. So first of all, if I react NaOH with the phenol, what's going to happen? What am I going to get over here? An O minus. Okay, so what happens is once I form that phenoxide, so this is a deprotonated phenol, which is called a phenoxide, just like a deprotonated alcohol would be called N-alkoxide. What's going to happen is I'm going to kind of get a reaction that looks like what happens when you take a Grignard and react it with CO2. So what can happen is this pair of electrons can come down here to form the CO double bond, and then have this pair of electrons move out to form the carbon-carbon bond, and then have this pair of electrons move there to the oxygen. So what I end up doing is I end up forming this compound as my intermediate. So I'm going to have a double bond, and then I'm going to have the C double bond O with the O minus. So I've added my carbon dioxide to the ring. Here's the issue. I've broken up my aromaticity, so I need to somehow regenerate the aromaticity. The way I'm going to do that is to lose this H+, and I'm going to end up then having that pair of electrons go back up there. So I'm going to end up forming the O minus, reforming the aromatic ring, and then have the deprotonated carboxylate on the other side. And then the H+, then this will pick up two H pluses, and we'll end up with the phenol, and now we'll end up with the carboxylic acid. And this is a pretty good reaction because what I'm making is salicylic acid. So this is a great preparation of salicylic acid, which I'm not going to take for my headache this morning because it'll eventually eat my stomach away. So I need acetyl salicylic acid, which means I need to put a C double bond OCH3 group on the ring to now form acetyl salicylic acid, and that is, anybody know what that is? It's a component of Excedrin.
Aspirin.
This is aspirin. So that's aspirin. Salicylic acid actually comes from birch tree bark. So there was a sort of homeopathic medicine that you could chew on some birch tree bark and it would help ease your headache. But then what they found was that too much salicylic acid would destroy the lining of your stomach, so they put an acetyl group on it. And then you had aspirin, and that was the chemist called Felix Hoffman did that. He did that for the Bayer company, or actually it's Bayer because it's a German company. And then what happened to the E? So that it became beta aspirin. Probably, if I had to guess, the most used medicine in the world. Who doesn't take an aspirin from time to time?
How would we go from that OH to the OCOO?
Oh, good question. How would we do that? I believe you are one slide away from the answer. One slide backwards. So how could I do that reaction? Kristen? We could use the acid chloride. Actually, the best way to do this is to basically react this with acetic anhydride. And we'll talk about this reaction. We're getting closer to that. But this is actually probably the way it would be done. But the way we just talked about it was using an acid. Was using a carboxylic acid chloride. Or
When you do the carboxylic acid chloride, do you have to protect the OH of the carboxylic acid chloride?
that's a good question. So could that acid chloride react with this and make an anhydride? Yes. The alcohol would be a little bit more reactive than that. So at this point in time, that would be okay. The other thing that you could do is you could just say, I'm going to do Fischer esterification. So you could use acetic acid and H+. And again, the alcohol would react faster than the carboxylic acid. And I could show you that in a minute why that would, or at the end of, maybe I'll show you why that would be the case. Okay. The OH on the ring has more electron density than the OH attached to a carboxylic acid. Okay. So that's sort of an industrial prep of salicylic acid that gets you closer to acetosalicylic acid. Okay. Now, the sort of last topic here of aromatics is what is called nucleophilic. Nucleophilic aromatic substitution. Not electrophilic aromatic substitution, but nucleophilic substitution. So nucleophilic substitution has everything backwards as far as nucleophilic versus electrophilic. So here's what I'm going to do. Here's an example. Let's say I have a chlorine on this ring, and I'm going to put a couple nitro groups here, and I could react that chlorine with ammonia, and I could end up then substituting the NH2 for the chlorine. That would be a nucleophilic substitution reaction. Now, this is what we would call an activated using an activated ring. So activated means exactly the opposite of what it meant in electrophilic aromatic substitution. So all of our deactivating groups are activating groups in nucleophilic substitution. And any group that it was an activating group in electrophilic substitution is now a deactivating group in nucleophilic substitution. So everything is opposite. So these nitro groups were deactivating groups. Now they are activating groups. Jacob.
Does the position they had change as well?
The position that they have to be in is they have to be substituted ortho and para,
Okay.
which is again opposite.
So does the halogen still add orthopara, or does it add
No, we're doing substitution now. So what I'm doing is I'm substituting NH3 for the Cl.
Okay.
So that's the substitution part. I'm not substituting for hydrogen, I'm substituting for a chlorine, or I could substitute for an OH group maybe later. So this is exactly the opposite. And so in order to be activated, the nitro groups have to be in an ortho-para substitution position. And so activated would mean that the ortho-para positions are occupied by withdrawing, electron withdrawing substituents. And the one we're going to use the most is nitro, because that's the one that's used for nucleophilic substitution. Okay. So I can do this, I can react this with NH3. I could also simply do this reaction with hydroxide. And if I did this reaction with hydroxide, I would end up substituting the Cl with an OH group. And I'm going to show you the mechanism with the OH minus. Okay. So I'm substituting, and this is an activated ring, so there's nitro groups at the ortho and para positions. So what would the mechanism look like? Here's what the mechanism looks like. So I'm going to write my chlorine here. I've got my nitro groups, which I'm going to go ahead and write out their full explicit I'm going to write out their full explicit structures. So here's what happens. The hydroxide group will come in and it will add to the carbon that the chlorine is attached to. But if I do that, then I have to move this pair of electrons over here. Well, actually, I'm not going to move it there yet. I'm just going to move let me erase, I will just simply use white to cover you up. I'm going to put the minus group onto that carbon. So I'm going to end up with the OH and the Cl attached to the same carbon. And I'm going to end up with a minus charge here next to my N plus, next to my nitro group, my N plus double bond O minus. So my question is, why does the nitro group have to be ortho and para? What is this nitro group doing to that negative charge? right here. What's this nitro group doing to this negative charge?
Is it pulling electron density?
It's stabilizing it by withdrawing electron density, and it would withdraw electron density how? Induction or resonance?
Resonance? Induction.
Both. It would be doing both, right? Because the N plus would be withdrawing electron density through induction, but then I could also take this pair of electrons and move it here, and then move that pair of electrons on the oxygen. So again, I never violate the octet rule, and if I did that, then I would have a double bond to the N. The N would still have a positive charge on it. So that's how it would be able to stabilize it through resonance, but also induction at the same time. Okay. So this is why to activate this group for substitution, I need electron withdrawing groups at the ortho position. The best electron withdrawing group is nitro. Jacob.
We're never going to have to show the resonant hybrid. Correct.
Probably not.
In this class, at least.
No. I mean, it's not that hard, but probably not. Because I've still got 2 more resonance structures that I can draw for this intermediate. Because I could take this pair of electrons, this negative pair of electrons, and I'm going to, unfortunately, I'm going to change colors here. Where did everything go? You're killing me. You've got to be kidding me. Welcome to Monday. There is no, that's the undo button. That's not doing anything. That's not doing anything. That's not doing anything. Okay, try it again. This O minus is going to come here, and then this pair of electrons is going to go to that carbon. So in other words, having the nitro group ortho and para, let's show how the para would look with the para. So now I've still got my OH and my Cl. I still have my NO2 group here, and now I'm going to have a double bond here, here, and I'm going to have a negative charge on this nitro. So I could just move the negative charge to the ortho carbon and then to the para carbon. Since there's 2 electron withdrawing groups at those positions, then it is withdrawing electron density and helping stabilize those 2 intermediates. Okay, so that's, and then there would be another resonance structure which I won't draw for this. So there's a total of 4 resonance structures here. There's 1, 2, and then 3, and then a 4th one.
Okay, this might be dumb, but how do you know that the OH is going to come in and get rid of the chlorine instead of like one of the nitro groups?
That's a good question. I don't know the answer to that. Because whenever we do these substitutions, the nitro groups don't ever get, The nitro groups are basically, I think, more stabilizing than they are to get rid of. So it's not one of those, the nitro group is not one of the ones that gets substituted for. But I don't know that that's necessarily obvious, other than we've talked about chlorine being a decent leaving group. So I don't know. I don't know that never happens. But in this case, we're gonna say the chlorine leads. Right. So if I want to form my final product, what's going to happen? What's going to happen is, let me come back up here to the first resonance structure, because that's the easiest one to show. So I've got my O minus here, and I'll just go ahead and put in my NO2 groups. And now I've got my Cl and my OH. So now my system decides, okay, I'm going to bring this pair of electrons back, and I'm going to reform the double bond. So who's going to leave? Hydroxide or chloride? Chlorine, because chlorine compared to OH is a better leaving group. So the chlorine will leave, and I will make my final product, which will have the OH substituted for the chlorine. So this is the mechanism for an activated ring. Activated ring means the ortho and para positions have electron withdrawing groups attached to them. So if I was to ask you to write this mechanism, and I could, I would say write the mechanism for this electrophilic or this nucleophilic aromatic substitution, and write all four of the resonance structures of the intermediates. I would not ask you to write the hybrid. So this is what happens with an electrophilic, or with an activated ring and nucleophilic substitution. And you can do this with you can do this with an NH2 minus, or you could do this with hydroxide, is typically how it's done. So that's nucleophilic substitution with an activated ring. And I think a couple of years ago, I think we were at or somebody came in to talk about research in a seminar, and they talked about potentially using this type of a reaction to clean up all of the TNT residue that's, I don't know, apparently in the ground at various places in the U.S. Mostly munitions depots from World War I or World War II, or where they exploded lots of stuff, because there's traces amounts of TNT, and so how would you get rid of the TNT? Potentially, if you could find something strong enough to come in and substitute that CH3, you could do this by some sort of nucleophilic substitution, maybe change it over to something that wasn't as explosive. But this would be an ideal situation to try and do substitution with, because you've got three activating groups in the ortho and para positions. Okay, what happens if you don't have those groups? If you don't have those groups, then you can take your benzene ring with, let's say, a Cl here, and just for the sake of argument, I'm going to put a methyl group there. And so then you say, well, I want to replace I want to substitute the chlorine with an OH group, and what you find is that you need extreme heat and probably a little bit of pressure to go with that. So when the ring is unactivated, you need higher temperatures. And what happened in this reaction is that when they took this parachlorotoluene molecule and they did nucleophilic substitution, they actually got two products. They got the OH ending up para to the methyl group, but they also got an equal amount of OH meta to the methyl group. So when you do a reaction like this and you get these two products and then you got to try and figure out your mechanism. Your mechanism has to somehow give you these two products. So this is an unactivated ring. So what does the mechanism look like here? Well, the mechanism here is going to be a little bit different. And so what's accepted for this mechanism is the following. And I'm going to do this with an OH, although they've also done this reaction with NH2 minus. So you can do this either way, and you'll see it either way. So next on the meta position, or the ortho position next to the chlorine, the first thing that's going to happen is under the extreme heat, the hydroxide is going to deprotonate that hydrogen. Run-of-the-mill reaction conditions, that's not going to happen. But under extreme heat, we can force it to. That's going to give me a negative charge there. And so then what happens is that this pair of electrons moves here and kicks off the chlorine. Creating the infamous benzene molecule. The benzene has issues. It's not stable. Why not? What's the biggest issue with this benzene molecule? David? What's the issue with the triple bond? Michael, is your hand up?
I was going to say, is it anti-aromatic?
If it's anti-aromatic, if I put that new pair of electrons into the pi system, but the pi system already is taken care of. So that's not the issue. What's the issue with the triple bond, Aisha?
Is it the triple bond is like cis and there's so much fluid there?
So what should the triple bond be in terms of geometry?
Oh, well, it's playing about, I was going to say it's kind of shorter too, so it would change.
It would kind of shrink the ring in because it's shorter, but the real issue is what should be the bond angle for a triple bond? Or what should be its geometry? It should be a 180-degree bond angle, or it should be linear. How do you put a linear system in a six-membered ring? If you do, it's going to be really unstable. So that's the issue. The issue is the triple bond would like to be at a 180-degree bond angle, and it's not. So the benzene is really unstable. But yet, this is the only way I can explain the next thing happening. And the next thing that's going to happen is that my hydroxide, my first equivalent of hydroxide deprotonated, my second equivalent now has two choices of where it comes in. It either comes in and adds here, at which point the pair of electrons goes there, and then that would form then the OH here with the double bond with the negative charge there. Or the OH minus comes in here, and then that pair of electrons moves that way. And is there any preference for the OH minus to attack either side of the triple bond? No, there's nothing really sterically there. So then that would give the OH adding para and meta 50-50. Which is consistent with the products that I see. So then in the final step, because there's water lying around, the C minus then deprotonates the water to form the meta-substituted product, and it would deprotonate the water to form the meta-substituted. So I don't know if anybody has any direct evidence of observing benzene, which would be really good and help prove this mechanism. But otherwise, it's sort of the preponderance of the evidence saying, okay, this is the only way I can get a 50-50 mixture of the OH group adding ortho and meta to this unactivated system.
Two questions. One, do you block the position to stop it from crashing?
You probably could, but you'd want to block it with a group that, well, if you block it with a group that, like another methyl group, that's going to deactivate the ring even more. So you might not be able to get this to go at all. So that's one way potentially to do it.
And then why does it pick that specific hydrogen in the first step to deprotonate?
Because
why doesn't it choose a different one?
Because that's the only hydrogen that when I deprotonate it will actually kick off the leaving group. So it has to be, that hydrogen has to be ortho to the leaving group in order to kick the chlorine off. Because otherwise, and otherwise, there is no leaving group. Right? The only thing that's left is the methyl is the leaving group or the hydrogen is the leaving group. Those don't leave. So that's the only, this is kind of like an E2 mechanism. So if this is your leaving group, there's only 2 beta hydrogens that could be lost. So this is the mechanism. The benzene is the intermediate that happens when you do nucleophilic substitution on an unactivated ring. So I don't remember if that was part of the homework set that was originally due today, but it'll be due Wednesday. But that should take care of all the reactions that were in that homework set.
So if you had a weak nucleophile, would there be no reaction?
If I had a weak nucleophile, there probably would be no reaction, or I would have to heat it even higher in temperature. So the two that we usually see are NH2 minus and hydroxide. And if we're looking at anything else, I mean, those are two that adding an OH and an NH to the ring are the ones that we probably want to do the most. And we want alternatives to the diazonium salt. So what these do is these give us alternatives to diazoniums. But before you get too happy and try and use these in your syntheses, remember that they only occur during fairly specific sets of circumstances. If you're going to do nucleophilic substitution on an activated ring, the groups have to be ortho and para. If you're going to try and do it on an unactivated ring, you still have to put the chlorine on there to begin with. So if I was to give you a benzene ring and say, let's say I gave you a problem and said, okay, benzene ring, I want you to make that molecule you would still have to have a chlorine on there before you did nucleophilic substitution to put the OH group on the ring. And will you see some of these problems on Friday? I mean, typically I do ask for a couple of these benzene to something for you to propose those reactions. So again, what you need to do is say, how do I add the OH group? To a ring. Give me the list. Okay, so diazonium salt plus H3O. How'd I get the diazonium salt on the ring?
Using a nitro group.
So it's put a nitro group on the ring, reduce the nitro to NH2, convert the NH2 to diazonium, add H3O plus, and you have your OH on the ring. Was that too fast for everybody to write it down? That's what we have our notebooks for. Except there won't be any page turning on Friday because there won't be any pages to turn that'll have the answer. Right? So we add NO2 first, convert it to NH2, convert it to a diazonium, and then convert it to OH with H3O plus. And no, I didn't give you the reagents for the first three because you'll have to look those up. But it's always those four together. Aaliyah? After you have diazonium, it's just H3O plus. That's how we always add an OH group.
Is that the only way?
No, because what do I have? Because what did I have on a previous slide here? Yeah, that's it. That's the only way. Unless you want to use the extreme case that we just did of putting the chlorine on there and reacting with hydroxide at 350 degrees. Would I accept that? Grudgingly, I would accept that because it's on paper, right? So anything on paper works. How do you put the methyl group on the ring?
You add BR and then MG.
Aisha? Friedel Crafts. I forget what's Friedel Crafts. CH3Cl and AlCl3. That would put a CH3 group on the ring. Is that the only way? No. But it would work.
On these homework problems, when it says NH2 minus NH3, is that the same thing that we were doing with just NH3, or is that different?
That's NH2, NH3. NH2 minus NH3 is basically NH2 minus, which is the equivalent of NH3. So when I did here, so this is NH2 minus, could be used to substitute an NH2 minus on the ring instead of OH. And coming back to here, this could also be NH2 minus. So if you look at the older exams and use those, as a practice exam, or, what do I have to know for Friday, you will see that I have asked, usually it's choose 2 out of 3, where you have to take a benzene ring and put the groups on the ring. So not only do you need to have to know how to add the groups, what order do they go in. Okay. And you'll see that some of them, and sometimes I act for a blocking strategy, which we talked about. So if you're not at that point, it's only Monday, but Friday will be here before you know it. If you have any questions, come and see me. I'll have your homeworks and quizzes on Wednesday. And I'll answer questions on Wednesday about stuff for the exam.